Distinguished lecture given by Phil Westmoreland. Phil is on sabbatical with us here for 6 months, and he is a professor at North Carolina State University, and previously he's been a program director at the NSF looking at combustion, fire and plasma systems. Rather longer ago than that, he got a PhD from MIT. He's been president of the American Institute of Chemical Engineers, and this is, broadly speaking, his research interest. So he's interested in kinetics and reaction engineering applied to energy, applied chemistry, polymer flammability, and so on. So a very wide variety of interests, and we look forward to his talk. So, Phil, over to you.
Thank you very much. Today I want to make the argument that all of us as engineers use molecular principles of engineering because the properties of matter are determined by molecular structure or atomic structure. The opening slide that I've chosen to use shows that it is a scale problem too. Here we have the moon, obviously enough. Less obviously, here is the space station, of course not rotating around the moon, but as it does a transit across the face of the moon. And at smaller scale still, the nucleus, the chromosomes, and the DNA itself that determines our lives. So the premise that I want to tackle here is that engineering creates innovations, it creates solutions to problems using a combination of physics and of properties of materials, conservation equations, and constitutive relations. Properties really sweep across all engineering disciplines, whether we're talking about the structure, the state, the thermal stability, transport, biological response, thermal diffusivity, mass diffusivity, performance of a refrigerant, the band gap of semiconductors. All of these things we need as engineers to bring solutions into physical reality. It's these molecular principles that I will describe that help us to correlate them, increasingly to predict those properties as well, to help us understand experiments and to predict results. So here what I will do is talk about first how molecular principles are used by engineers to create exciting technologies, and a little bit about what we mean by exciting technologies. Second, the sorts of ideas and tools that can be used. Increasingly, they are easy to use. Some might say dangerously easy to use to get an answer from, but very powerful. It does help to know what's underneath it. I will not spend a lot of time on the theoretical underpinnings, but of course it's very important as far as getting results that are useful to understand what's behind it. And then I'll wrap with a series of applications from spacecraft thrusters to propulsion, engine design, to new refrigerants, to the juxtapose issue that turns out to be the same sort of topic, polymer stability, thermal stability, and making biofuels by wood pyrolysis, where we'll see that experimental and computational tools are very similar. So I want you to think of a few exciting technological advances. Certainly the connectivity that we have throughout the world right now is a result of those technological advances. That I can meet with my students back in North Carolina or my research collaborators in New York, in Paris, in Saudi Arabia, is a testament to that through the variety of interaction technologies that we have. Likewise, the sort of visualization techniques that we have come on a whole variety of different devices, increasingly many of them mobile. Another area that is inextricably linked to the issue of computation is 3D printing. This complex little do-nothing, but interesting little toy was printed by 3D printing. Increasingly of use, and now even of use in printing three-dimensional tissues. This is from a company, Organovo, in San Diego, California. Indeed, the variety of different ways that we can use biology, both for biological purposes themselves, physiology, health, medicine, but also to create biomimetic technologies, or even to use things like DNA as the building blocks for structures and even for computation. And of course, as far as health, the development and production of new medicines, indeed, manufacturing in general has never been more important, but there is a renewed understanding of how computation affects that. Finally, big data and analytics creep through all of these topics. Those are all very exciting developments. Consider dropping back. I pulled out a Wired magazine from August 2002, where they were talking about the hot developments in 2002. Consider where they are now. Biometrics, Bluetooth, PDA phones. I've got the health app on my iPhone. Of course, it can be hooked to the Apple Watch as well. eCash, well, there's Bitcoin. But of course, Apple strikes again. Apple Pay being accepted now by the tube at different tube stops for electronic payment. Segways, finding niche use, shall we say. So everything that's exciting doesn't turn out to have the same impact. But voice recognition, you may get a person on the other end of the phone when you speak to it, or you may get voice recognition, or it might be on your own phone itself, such as Siri. And of course, I alluded to Skype already as far as voice over internet protocols. And of course, wide area protocols and Wi-Fi are widespread too. As we think about other innovations that we're creating, let's look at them in terms of Wired's configuration of the hype cycle. Gartner is a consulting company that developed this hype cycle, and you can see these different items that we mentioned at different stages. Initially, at some sort of stage of hot, new excitement, starts to be talk about it, and then it gets a little overinflated, starts to appear in James Bond movies and so on. Inevitably, often enough, then there's a trough of disillusionment that sets in. If a technology does have potential, often it will climb in the slope of enlightenment, as Gartner called it, onto the ultimate plateau of productivity. So you can see where some of these were. At that point in 2002, biometrics were headed for a fall, in Wired's opinion. PDA phones, or smartphones, were on the downslope. There had been great enthusiasm, then there was a feeling, no, it's never going to amount to anything, where I felt it might come back up, and so on. You can see how these things develop. How we turn hype into substance is using these different analytical tools, but using properties to actually come up with the results that we want. Solar panels, much talk about the food, water, energy nexus. The Martian has been a big hit in movies this year, the notion of interplanetary or lunar exploration, microelectronics anywhere, and even, as I've discovered during my time in Great Britain, the cup of tea. Let me focus on the cuppa. Here we have a widely sold drug, as one quote said, the world's most widely consumed psychoactive drug. Now, here we have caffeine, and here we have caffeine. Here we see the individual atoms, but if you were to look at the molecule with an atomic force microscope or some sort of capture, you'd see the electron density around it. And it's the differences in the way that structure interacts biologically that determines how it behaves. Now that's relevant to engineering, partly because it's so much like adenosine. If you look at these two pictures, these blues are nitrogens. You see a very similar structure here, this 6-membered and 5-membered ring, to adenosine. Well, adenosine is something that we all like to have. It lowers the heart rate. It helps us go to sleep. It does so by docking, by fitting in with particular interactions within a complicated structure called the G-protein coupled receptors that, in this case, are on the lipid bilayer, the membrane, cell membrane of nerve cells. So adenosine docks into here, the receptor triggers action within the cell, and the mouse goes to sleep. That's good. Other times we actually want to be a wide awake, jittery, jiggly mouse. As it turns out, the caffeine also docks on these receptors. It inhibits the behavior of the adenosine. So that's all nice to know. But as engineers, perhaps we want to do better packaging. What do we do to keep that? Perhaps we want a better molecule than caffeine. More active, less active. Maybe we want to decaffeinate. We need properties for design. Shifting gears, but still with this idea of molecular principles, let me recognize Sir Hugh Ford, whom I've read a lot about. He was very much involved in the first polyethylene manufacturing plant. At the time that he was doing that, high temperature and high pressure were required. But now the approach is to use homogeneous catalysts mixed in that are used to create very regular polymeric structures, not just randomly patching it together, but specifically patching it together. And if I write down a formula like this, you have no information at all to go on about how it's working. But if you compute a structure, if you look at the structure and say, oh, well, here's my catalytic atom right here. Here's an ethylene that's bound by the two arms, the two ligands from that ion there. And you have these side pieces. Well, this first ethylene comes on. The molecule actually moves to one side. You pick up another ethylene. It sticks them together. It's almost like a childhood game of stringing things together. Furthermore, these big flappers here steer the structure, so it was very regular, almost ratcheting it into a structure that would be regular, that may be low-density polyethylene, high-density polyethylene, low-density polyethylene, and so on. One more general example. Modeling can now begin to describe crack formation. We have many mechanical engineers here, and you understand how important crack formation is to the behavior of a material. Here's some work, I believe, from King's College that does multi-scale quantum mechanics and molecular mechanics using different types of theory in different parts of the problem. Quantum mechanics, where you need the accuracy, and then molecular mechanics, where you simply want to follow how things moved. Here in orange, we're showing boron, so the notion is to try to understand how that propagation occurs, and of course, it must be in 3 dimensions. So we have tools to be able to do these sorts of predictions, these sorts of techniques of understanding measurement. And despite the fact that I would insist that computation is very helpful, the reality is that accurate data are best. Why? Because nature is more inventive, certainly, than I am. Nature comes up with surprises. We need to work for accuracy. That means comparing against other measurements. We also need to characterize the uncertainty, because there is uncertainty in every measurement. Yet once we get the data, usually we have to correlate. We want to interpolate. We want to extrapolate. How do we interpolate between 2 points if we don't know whether it goes linear between them or very non-linearly between them? Well, we need to know something about that. So what relations do we use? Perhaps we're able to infer a structure the way the ideal gas law was derived. But you come back to saying what variables as well as what relations do we need. We may get lucky. The variables may be obvious. The relations may be linear. Often enough, we're not. Now, what do we do? Well, usually what we have to do is take some theoretical foundations, perhaps an idealization, but then we come up with an understanding of what sort of behavior there might be, what sort of correlation we might strike. An example, Joe Hirschfelder's equation from the 40s, derived from kinetic theory of gases to look at gas mass transfer, gas diffusivity. And the structure here, well, there's a leading constant we can fit. There's different forms. But what happens if you have a mixture? What happens if you have something that has more interaction that's considered? That does not invalidate the usefulness of this approach. This approach gives often a basis for saying what types of dependencies we should look for, how we can fit a correlation. If we want to move towards prediction or predictions that we can use to compare against data, ultimately we have to know that properties depend on structure of materials. I show this cartoon to suggest the two major branches. One is using electronic structure theory, the other so-called molecular simulations. Molecular simulations could be used inclusively, but more commonly it's used to describe a physical, mechanical sort of description, typically based on Newton's second law. I show these different covered mountains to reflect that the ab initio calculations really need to be done at 0 kelvins. Not necessarily, but perhaps even in the gas state. Not gas per se, but molecules not interacting with each other. Of these so-called ab initio methods, there are wave function methods, there are density functional methods. They have the same roots. They're different sort of approaches to the problems. Distinct from the level of theory, though, is the description of the atomic orbitals that are used, basis sets. So if you want to sit down and run a good calculation, I can have you doing it in about 5 minutes by telling you what theory basis set you should use. You have to learn more about whether that's an appropriate basis set, what you should use. But again, there are computational tools that make these very easy to use, easy to get results. As a friend of mine at Shell told me, we used to worry about convergence. We used to worry it was so hard to use these things. Now they're easy to use. You're worried about the results that you get. He said, we were worried about it being user-friendly and foolproof. He says, now the challenge is to make it foolproof and user-friendly. So that's a good thing. That's a better stage. We can actually get to the results of the problems. On the side of the molecular simulations, they're so-called Monte Carlo simulations or molecular dynamics, and the analogy to basis sets is the potential energy functions, but those are things that we are familiar with, Hamiltonian type structures, and it's stat mech that really gives the properties that we need. In the case of molecular simulations, at least molecular dynamics, we've got the classical Hamiltonian, kinetic energy plus potential energy, in terms of the coordinates q and the momentum p for each atom, each particle in the system. We can solve that basically to follow how atoms move around in space, reevaluating constantly how the position vector and, for that matter, the potential energy is changing as it moves in the environment. Much more concisely for electronic structure theory, H psi equals E psi. A distinguished computational chemist that I got to be friends with at MIT said as a high school student when he was introduced this, he says, well, why don't you just divide through by psi and you have E equals psi? Well, they're functions, okay? But the point is that at the face of it, it's like E equals mc squared. There's a very simple summary of what's going on, but how you use it is important. Also considering that we do need to span different scales of time and of space, from atomic and subatomic scales up to galactic scales, from times that are femtosecond sort of range up to hours, days, years, millennia. As it turns out, many of these methods fit well into certain domains. Quantum mechanics, both in terms of computational time and suitability for the problem, really is for very small scale. StatMech relies on having an assembly of molecules, atoms, particles that can behave statistically. And continuum mechanics, again, requires that we have a continuum. So the business of handling scales traditionally in engineering has been, we find something at this scale, transfer it to here, do those calculations, transfer it up to there. Maybe some we can get, say like a dipole moment at this level, transfer up to the continuum scale. That's all fine. There's been some remarkable work in the last few years in China, in the group of Jinghai Li at the Chinese Academy of Sciences, working on an energy minimization principle that is surely based in thermodynamics. But the notion of how we deal with these multi-scales simultaneously is important. Interestingly, the problem they focused on is not a molecular problem, but it's fluidization technology, gas solid fluidization. So it's easy to get fairly simple properties like interaction energies. Here's simple as simple can get. Argon interacting with argon. But what you see as far as this dotted line is the Lennard-Jones potential, a fitted potential based on transport properties. And these different lines show that different levels of theory, which are represented here for a common basis set, different levels of theory do, some of them do remarkably well, and some of them do terribly. So knowing what type of level of theory is appropriate for the question that you're trying to answer is very important. And yet, we can do very well. I sit on an IUPAC standards committee for radical thermochemistry, and we find that if you take the set of all experimental data and look at the refined uncertainty, some of the theoretical methods always hit within that bullseye that's there, which is very, very exciting for an old experimentalist like me. So what we need to do, though, to get thermochemistry and kinetics is to find the geometry, to find the structure where if we're looking at a general sort of potential energy surface, then this lowest energy level, where you're at a minimum with respect to all position coordinates, is where we want to be. If it's a transition state, it will be a minimum for all but one degree of freedom, the reaction coordinate, the way that the molecule is changing. So that transition state can be related by reaction theories based on statistical mechanics to give us rate coefficients, to give us rates of reaction. And of course, it really matters to us about what we're starting off with and what we end up with as well. So in terms of doing the calculations, when you use quantum chemistry and StatMech, often it's not just finding the reactant, the product, and the transition state, but showing that the transition state is the right one. Well, first, finding the transition state, but then confirming it's the particular transition state of interest, and then including complications as necessary. Again, it has come very far as being able to do that. There are free codes, there are commercial codes, there is support, there is do-it-yourself, different approaches by which you can come up with things, again, from docking of an enzyme into a structure to predicting a thermal conductivity that you need or the like. Let me shift and look in the last set at a few applications, though. I'm a reaction kineticist, so I'll refer to several of those, but there are a lot of intersections across the engineering disciplines, as is the case in the first one, this business of looking at spacecraft thrusters. The International Space Station could not quite fit in the courtyard outside here. If we took out the big blue building, it would just about fit in there. It's some 250 feet by 350 feet in rectangular shape. And we show a spacecraft docked in there as it's passing over. How do we keep it in position, we as society? Well, it's by using thrusters, jets of gas that puff and then push things over in one direction. Well, of course, it's actually creating gas by injecting a liquid fuel like monomethyl hydrazine, a very nasty base, with a liquid oxidizer like fuming red nitric acid, a very nasty acid. The big danger is not to the astronauts, it's to the people on ground loading up the supplies. But what happens when you throw an acid and a base together in the chamber, it generates gas coming in here and thrusts out gas, ejecting it, causing the spacecraft to move as a result. It would be really nice to come up with something a lot safer than these two reactants, safer to handle. So a group of us were working together under the sponsorship of the U.S. Army Research Office to try to come with alternatives, new reactors, new thrusters, and new reactants as well. But first you have to figure out how it works in the first place. So to do experiments is a little bit tricky. You can't really allow the oxidizer and the fuel to be in the same place in the room except where the experiment is taking place. One case where it can be done, though, is to take a drop, here shown at the top of the screen, and drop it, the monomethyl hydrazine, into this little pool in a little cuvette of red fuming nitric acid. Okay, so it drops through. You see a haze build up around it. As there's gas-liquid reaction, it hits the bottom and, okay, it sort of bounces off. Nothing happens. Well, why is that? Well, it did split up. There's a satellite particle going off. But again, that touches down. It settles in a little bit more, and suddenly we start to see things beginning to take off. This one is rolling around on the surface. But as this big drop comes in with its extra momentum, we see, boom. What's going on there? Well, if we're going to design a better thruster, we better figure out what's going on. It's a combination of the equipment design, computational fluid dynamics, and key elements of the chemistry. But it turns out the chemistry is very fast here, so the rates don't matter. But what you make, how much gas you make for a particular amount of oxygen, that matters. So we developed a model recognizing that there has to be the gas kinetics, liquid gas, and liquid-liquid kinetics. We came up, it was fairly straightforward. We said monomethyl hydrazine, you get OHs pulling things off, NO2s, and it goes down to CO and CO2 stepwise. Those are the key details that you need. Again, it's very stepwise. There's not a chain branching reaction like you have in hydrocarbon combustion, but in running the gas kinetics and starting off at temperature, yeah, we were able to match up with a reduced mechanism what was there. We were able to test against shock tube data, show that it worked reasonably well, with one rub. It turns out the models didn't describe the ignition itself, just what happens after it's ignited. So there were two essential insights that came out. Based on the experiments, such as what you just saw, we could infer that we have a Leidenfrost effect. That is, that as things approach, they immediately give off gas, just like a water droplet on a frying pan bouncing off. As it gets close enough to generate gas, it's pushing it off the surface that's there, holding it off the surface. The bump into the air wasn't the result of that, but certainly the little satellite droplet moving around the surface was an aspect of that. It turned out that the ability to model that depended on our being able to say what the stoichiometry was, how much gas was given out for a certain extent of reaction because there's no mixing. You're putting the two things together that react instantaneously to give off gas. They don't mix together. So first, we came up with the stoichiometry that was there. Not having access to experimental measurements of the gas coming off, we're able to do modeling and prediction of that. The second key element, though, was the liquid-gas reaction. What's going on there? Because, again, you saw after the liquid-liquid contact was made, there was still no ignition. It turns out that the key element there is that the gas coming to the liquid is mass transfer limited, but it begins to be exothermically absorbed into the liquid, and the solvation energy determines how fast the liquid heats up. We had to come up with the stoichiometry again that showed with, say, monomethyl hydrazine reacting with the nitric acid liquid would form a complex first, not react explosively, but form a complex. Addition of other nitric acids would form a bigger complex until finally, due to all that solvation energy, you see a separation of the nitric acid into a plus coordinated with the MMH and an NO3 minus. That could then come apart, generating, in effect, the gas phase MMH again, but for nitric acid gas molecules. How well did it work? Well, here, putting the CFD model, putting the chemistry together, we're able to describe the time scale reasonably. We're able to describe things that corresponded to the high-speed video that we're able to take of these experiments. At least my mechanical and aero colleagues at Purdue University were brave enough to take the high-speed video of it. But again, it was all consistent. It made sense. And it was a combination of trying to understand these properties of the materials, the properties of how they interacted, as well as the continuum behavior of the CFD that went on. Second example would be looking at combustion experiments for engine design. Here, it turns out that the same NOx kinetics that we developed for the gas phase in the hypergolic fuels is relevant to low NOx engines. Pratt & Whitney and GE have been using that, particularly since they're interested in much higher pressures, 50 to 75 to 100 atmospheres, higher pressures than data have been collected at. In fact, they were having to sell engines that they could not build yet. But what they've described is that rather than burning metal, making prototypes 50 times at $2 to $12 million, even if you just want to move an injection nozzle a little bit, that by doing all those gentle moves with CFD, they can do it in 2 engines and come up with the final production. So in similar ways, looking at hydrocarbon fuels, oxygenated fuels like biofuels, halogens and the like, all these aid the ignition and performance models. In my group, we tend to mix an experimental technique called MBMS, molecular beam mass spectrometry, with theory and with models. The base, though, is this hypothetical, freely propagating flame. Let's say we gave Dr. Cawley a nice sheet laser to fire off, and we filled up the room with methane and oxygen in a combustible mixture. Don't do this experiment at home, folks. And he fires this off. What would happen is that you'd see a sheet moving across here, a sheet of flame moving across, and if we stop and look right now, we would see that on this side it's unburned gas, here it's burned gas. The temperature rises up to a high temperature. Remember, we're saying adiabatic. That adiabatic temperature is very much characterized by the thermodynamics, nothing to do with the rates of reactions, but the speed at which it propagates. Very much an interplay of the transport physics and of the reaction chemistry going on. And indeed, there are reactants being consumed. products being formed and intermediates being formed and consumed. So to create that experimentally is a so-called flat flame burner run at low pressures. Here's a physical realization of it. You see a flame burning on the surface, not very thick, but by operating at low pressures, we can expand it physically enough to be able to do gas sampling, not by moving a probe, but by moving the burner and the flame relative to the probe. By expanding this gas into a 10 to the minus 3 chamber, collimating it with another orifice into a 10 to the minus 7 torr chamber, 10 to the minus 10 atmospheres, which 10 to the minus 10 bar. What you can see is that we create a beam of molecules. These are not colliding. These have gone to free molecular flow. And of course, if they can't collide with each other, they can't react with each other. If we've expanded them and of course cooled them, they have too little energy to fall apart as well. So we can look at very reactive species, including radicals, fragments of molecules with broken bonds, and get these sort of data. Here's some classic data that we had done with simple ethylene oxygen, fuel-rich with argon. See the temperature rise, the experimental temperature. Argon is not being reacted, but the number of moles are changing as we generate products. So it's diluted down by that. But you see oxygen being consumed, ethylene being consumed. Actually, oxygen and ethylene aren't being consumed in this region. You've got back diffusion of material back towards the surface, but the mole fractions change, just as we saw the change in the argon. See carbon monoxide, you see water and CO2, and you see molecular hydrogen and the radicals H atom, OH, coming up with very good signal to noise ratio there. In fact, for many species, here are just the C3s, because C3H3 has been strongly linked to making aromatic pollutants, soot, if you will. In this particular flame, 41 species with the old instrument that we had. We now use 2 systems, one at North Carolina State with electron impact ionization, but another one at Lawrence Berkeley Lab in California, where we're using single photon ionization using the advanced light source at Lawrence Berkeley National Lab, intersecting this molecular beam. See, here's the source, the sampling probe, the beam going through, and with a light beam in the vacuum ultraviolet range. That's at the sorts of energies, 8, 9, 10, 12, 15, 20 electron volts that give enough energy to pop off an electron and make a methane plus out of a methane. Mass spectrometers need positive ions to be able to analyze. Okay, and here we're using time-of-flight mass spectrometry to do the analysis. So we've come up with a number of discoveries, one particularly to highlight where we did make the cover. You can see it's different geometry from the experiment because the aspect ratio of a magazine cover has to be this way, not this way, but that's okay. The point is that it was there because of the signature event of finding out that this pollutant had been present all along, had not been detected, because all the analytical techniques that had been used have an interference between it and acetaldehyde. Here, though, we could even split up and say 37%, 63% out of the total was the ethanol vinyl alcohol or acetaldehyde. So again, with this precise resolution of being able to look at the threshold when ionization turns on, we're able to discover this. But to map out many species, now I'll show just one, tetrahydropuran is the same sort of 6-membered ring, 5 carbons and an oxygen that's present in glucose, in cellulose, in many biofuels. And you can see, again, showing the different species. Now the lines here are models. They're not fits through the line. They're models. The model is not adjusted, and yet the prediction is quite excellent on these different species that are here. When we get down to the minor species or lower concentrations, the fit is not necessarily as good, but for these species where we can't do a direct calibration, I mean, you can't just put in a methyl radical from a cylinder into a tank. The uncertainty is a factor of 2 or 3. In many cases, the shape similarity is really saying what a good job it's doing. But of course, the purpose of this is not just say it does well or it does poorly. If it does poorly, that gives us an incentive to try to figure out why. If it does well, we can begin to probe how the reaction mechanism is taking place. Again, here's the tetrahydrofuran I said, the 6-membered ring with an oxygen. And because there are hydrogens at each of these vertices, different hydrogens can be pulled off that position or that position or that position. And then the molecules can decompose. They can break down by well understood routes. Furthermore, the thickness of the arrow allows us to say what are the dominant routes that were pursued. These dotted lines says, no, not really much. But on the other hand, the thick line is saying most of it is going through this, through this, through this to ethylene, to vinyl and acetylene, and to formaldehyde, and so on. So we can pick apart how it's going on, also giving us a sign that if we're expecting to get a better understanding of this reaction, we won't see it from this experiment. We can from this experiment. Case 3 is related to that, but it's saying how do you come up with ozone-safe refrigerants? Well, again, the problem had been ozone depletion from the chlorofluorocarbons. By making hydrofluorocarbons, you take out the chlorine and you put a hydrogen on there that can be removed as you go through the troposphere. Part of the problem with chlorofluorocarbons, they're so stable, so safe, that they can make it through the troposphere to the stratosphere, where they could be broken apart by ionizing radiation. So now getting low global warming potential is an issue. One choice is so-called YF, propylene with 4 fluorines at these positions. HFO 1234YF is the jargon name for it. The point is it's a hydrofluorocarbon commonly called YF. So there's the question, okay, once we've passed ozone depletion, once we've passed low global warming, is it dangerous? Is it flammable? We thought not, but we were convinced to develop a mechanism to find out. This blurry thing off in the corner is following the same sort of logical steps that I said before. If we have decompositions of molecules, we know it will be by breaking bonds apart directly, thermally, homolytically, or by so-called pericyclic concerted reactions, where things come across all at the same time. Or if we have radicals, they can unzip. Beta scission reactions, abstraction. So there's a finite number of specific reactions. We can enumerate them. We can put parameters with them. We can do computational chemistry to get the specific rate constants, the specific thermochemistry, and compare it to literature data. As it turns out, there's only one set for YF of any flame data that we could find in the literature by Takizawa, who did caution that experimental uncertainty was rather large. Nevertheless, the agreement of this study is sufficiently good. It's way down in this order of 10 centimeters per second range that says it's pretty non-flammable, not too much to worry about. So again, we were able to see this low flame speed suggesting it's important, but it also showed that HF, hydrogen fluoride, was being produced. So illustrated the sort of pollutant issues that come up. The final case, a double case, is looking at the polymer stability and making biofuels. If you're trying to look at fire-safe polymers, you want them to be stable. If you have polymer flammability issues, you may simply want not to be stable, but to give off non-flammable gases. And then making bio-oils, most common use right now, most common approach is to flash pyrolysis, flash heating. So here with plexiglass, here with lignocellulosic materials, the cellulose representing a very stiff crystalline chain that gives the strength to wood. We will tackle that using experiments and modeling to look at things that are very important to us. Fire-safe aircraft interiors. airplane fires are infrequent. They only happen pretty much on the ground, landing or taking off, or just after takeoff. But for those of us who travel a lot, it's really important that it be as safe as possible. Right now, the escape time in a standard test is about 5 minutes. And that's one reason why there's so few problems. But of course, as engineers, we know that the standard test is not necessarily how things may happen. So extending that to 15-minute escape time would be ideal. So we developed flammability tests for different scales. You can do it actually in an aircraft. The Federal Aviation Administration in the US takes a big hollowed-out DC-10 and sets chairs or seats on fire. There's so-called cone calorimeter that still takes about 100 grams. And if you work with any polymer chemist, they do not want to give you 100 grams. For them is a lot. They want to give you a few milligrams, sort of the bottom of a test tube amount to test. So we came up with two methods. One, working with the FAA, of a microcalorimeter, and second, in our own lab, developing a combined TGA-DSC, thermogravimetric analyzer, differential scanning calorimeter, with gas analyses, and then could calculate the enthalpy of products that were made. Turns out the methods correlated very well. Here's so-called peak heat release, the number that we calculated. Here's flashover time. That's the catastrophic event that correlates to cabin escape time that you want to be way over here with. And you see we were able to achieve a really good time. Furthermore, comparing the cone calorimeter and the flow calorimeter, the FAA calorimeter, and then the one that we had in our lab, you see very good agreement between these different techniques by understanding molecularly what was going on there. Furthermore, we could rank the flammability. All these with asterisks are ones that we had developed as improvement. You see some of them quite good. And we could classify them by the type of polymers, allowing the polymer chemists to develop new polymers that would be fruitful. Then finally, with the theoretical methods, we used the molecular dynamics method, or a new one that we had created with reactive force fields. In this case, acting on plexiglass. And you can see methyl groups rotating around, maybe. Methyl groups rotating around. You can see bonds stretching. And what would happen is that this stretch would pull it apart, and then it would snap back together because they have to move out of the way. Eventually, the molecule does disrupt. And what we found is that the activation energies not only agreed well, but by studying this, we could see that the bonds were being ratcheted together as the polymer had its internal random motion, or ratcheted apart, describing how the physics and the chemistry were coming together. With cellulose, it's just another polymer. It's a very regular polymer, though, as it turns out. The reproducing unit is a glucose unit. There are these single oxygen bridges, glycosidic bonds, that connect the different segments. And if we look at it from on top, you can see it's extraordinarily regular in structure. If we rotate it, you can see from side, it's also very regular. In fact, all the hydrogens stick up or down. That allows hydrogen bonds and other connections to make a crystalline structure present. So from new data that we took, we were able to develop a network of reactions saying that apparently, because of work that we did with liquid chromatography, mass spectrometry, the cellulose chain itself thought to undergo an activation state, becoming molten, but then breaking at this bond to make levoglucosan, this double ring sort of structure. Well, we took that information using a new analytical tool, GC by GC mass spec, compared to conventional GC mass spec that I know some people here have used, where this mixture here in conventional GC mass spec gave 200 species. We had 750 here. So carefully identifying after the reaction, shooting it into this GC by GC system. And this big peak here, think of it as a contour plot. The red says it's very high, is levoglucosan. what we showed was that the way it breaks apart is that OHs elsewhere in the molecule can catalyze the decomposition. So as it breaks apart, you see two waters being formed, this ring being formed, the levoglucosan. I won't go into it in detail here. I'll just remark that next month I'm giving a Leverhulme Trust lecture in chemical engineering, and we'll talk a bit more about the biofuels. To close, in conclusion though, what I've said is that molecular principles are of use for understanding properties that all of us as engineers care about. Then I showed applications of the tools for understanding experiments and for using calculations in these 4 topic areas. Again, I would close by insisting these tools are increasingly useful because of their ease of use and because of their accuracy. And of course, I must thank the loyal graduate students who've carried out so much of this work, my funding sources, and a lot of supercomputer time. Thank you very much. Do you have time for any questions?
Yes. Guillermo has a microphone, so questions, please. So I'll start by asking one then if nobody else will.
Go ahead.
Okay. Is this live? Not sure. Is this live? Okay. So, as I understand it, most of the computations you showed there were quite small scale. Presumably in things like a diesel engine, where you're worried about particulates, for example, or NOx, then you've got the interaction of rather larger scales. So how does that play out?
I was recently doing a calculation over Christmas on a pretty big molecule, a triethyl phosphate, that took 45 CPU days at the level of theory we needed to go to. So depending on the level of theory, even a very small system, well, that's actually pretty big for quantum mechanics, but even a small system can take a long time. That's why playing with the different levels of theory, testing against data to establish whether a low level of theory is good enough, but then figuring out ways to span scales. We did work with Dow Chemical when they did a fairly big calculation simply to get one Benson group so that they could extrapolate to many different compounds that were in their product ensemble. So they invested a lot of money in one calculation, and then through correlation were able to expand it. So it's still impossible to run a huge calculation, where huge depends on what you're after. You can't run quantum chemistry for a big system. You can't run molecular simulations for a few picoseconds. A nanosecond is almost beyond belief. So there is this trade-off that you point to that's inevitably present. How do we span those scales?
Thank you.
Thank you. Phil, one thing that is always of concern is level of accuracy required. We start looking at the material scientists often use large slabs of material with, how should I put it, density functional theory approximations that in a homogeneous gas phase would not be acceptable because there are other constraints on that. So where do you see that going in terms of embedding methods and the level of accuracy across fields and so on and so forth?
I think very much along the line of Dr. Colley's question, the how do you deal with these multiple scales? There's some remarkably powerful ways. Again, I've been especially interested in this Chinese Academy of Sciences approach, where the approach they found actually scales very naturally on parallel supercomputers. Beyond that, though, it's a matter of simply being smart, just not throwing more energy. So we were talking about different levels of theory. Keiji Morikuma of Japan and of Emory University developed a powerful method called ONIOM. That's like onion, but with an M, to conform to the acronym that they came up with the words behind it. But the idea is very much that you take the central active core and then put on layers with lower levels of theory that are more affordable. So you do a calculation of the small part at high level and at low level. the larger part strictly at low level, and you extrapolate. The quantum mechanics, molecular mechanics method that I showed for crack propagation, very similar. In fact, I think that's conveniently right there. The dark blue are the ones who are treated at high level of theory. The gray or light blue atoms were the ones who were treated at low level of theory. So this idea of coupling scales at the point where it doesn't matter that you're not being atomically specific or electronically specific is one, I think, very smart way that it's being applied. Companies are using this, actually in many cases, more than academics are. So this is a case where the companies are actually ahead in use of some of these techniques ahead of us in academia.
Other questions? Ricardo.
Thank you for the talk. Again, it's probably a similar question to the one just posed. So I went to a symposium by BASF, 150 years, last year, the year before, and I was blown over by the sort of the work presented over 2 days. A lot of it was to do with the creation of new materials, new compounds.
Yes.
I mean, you probably know what they do, but you know, to me as a mechanical engineer, it looks as if you could just about do it, and you can just create as if you could bring a number of molecules together, a new compound. I'm not sure, again, the difficulty is how you translate it in a time, in computational resource, in just the intelligence to create a low order model. You haven't discussed that very much, but I just wondered whether you had any comments, because it looks as if it's there, and I just wonder whether we are there, and I somehow doubt. But
in some cases, we are definitely there. I think where you have very regular materials, of course, if you can look all you want to at the molecular structure or the atomic structure of a metal, but the grain boundary is determined so much about how it actually behaves. Again, handling different levels of theory that are appropriate to different sort of points means that we can do quite well with some materials. There is a rather large US initiative called the Materials Genome Initiative that comes out of an initiative that I started when I was at National Science Foundation, but because I was involved at the beginning, I followed with great interest. And people are able to do, I mean, classically in material science, you might check the different structures. High throughput screening has been a boon for that, to be able to try many different things, but both in drug discovery and materials discovery, the initial joy over high throughput screening turned to the realization that everything is still a big number. So you do know things about it. You can do a guided search for things. And for the right materials, you can find a lot. Yet, just a few weeks ago, I saw some extraordinary work on highly structured materials, zeolites, where a new corresponding structure to a natural structure that exists had begun to be probed. There was a science article, there was all sorts of new insight. So the ability, again, in many cases with theory and with our understanding of the fundamentals, is how to be smart. As engineers, I hate to tell any student who's not aware of it, if a correlation is good enough, then you don't get to study why it's happening if you're in industry, because it's good enough. But if it doesn't work, and that often happens, then the company will want you to figure out why it's happening, and there you have to fall back on your theoretical understanding, because engineering intuition, after all, is not an inborn thing, it's a learned thing.
Very true. Other questions?
Yes.
You gave an excellent example on the flammability in the aircraft. Is already serious interest from the industry, either from the chemical industry or from the aircraft industry, to apply it in that way?
Oh, and the electronics industry and the biopharma industry. There's a great deal of interest in that, a great deal of activity. I ran a study in 99, 2000 for a group of US agencies about how molecular and materials modeling was being applied around the world. And I found to my surprise that DuPont in the 1960s was trying to compute how biological molecules, how new drugs could be created. Again, they've been through ups and downs, but there's still that interest. Again, the same sort of thing that that Ricardo and I were discussing a moment ago, the idea of using the initial insight and then exploring around that insight to find out what direction is going to be fruitful. It's that combined approach of what we know and what we know about the direction to go to that's most important. A colleague at Eastman Chemical, who was in process development, was bringing out the point that accuracy is very important, but precision, when you're at the development stage, may not be very important at all. If you can have the right trend and saying which way to go at the development stage, that's more important than having an exact number. On the other hand, if you're trying to design how thick your pressure vessel should be, yes, you put a margin of error in. If you're interested in how exothermic an explosive reaction might be, you may want a good tight number, but again, different scales of time and of space, different needs for the amount of precision. You do want to have an accurate number, or at least an accurate trend to be able to go from, to be sure. But industry has been very actively using it around the world, and a big conference at the end of September, I heard some amazing things coming out of BASF about how they were using some of these techniques. Yes?
You spoke briefly about sort of Pratt & Whitney developing engines, certainly jet engines, for the aircraft industry. When they were designing engines for supercruise, when they were operating above the speed of sound without using an afterburner, did they have to use computer models in that sense to work out how the air would interact with the fuel in the compressor stage? Because obviously they hadn't done that before.
I don't know, but I'm sure they did. And again, you're right. It's different things. You need to have essential features of the chemistry. For many years, the computational fluid dynamics people would say that we'd rather not have any reactions if you can just give us one. Sometimes that's enough. Other times it's not. If you're trying to get the overall heat release, one reaction may be enough, so that you can do in a complicated environment, such as you're describing, you can do the calculations. If you're interested in whether the security aircraft, the intelligence gathering aircraft doesn't put out a smoke trail, then you have to go to another level that's there. And again, another issue with jet engines, with aircraft turbines, is that if you form in a terrestrial burner, making lots of soot is good so long as it gets burned out, because the radiation heat transfer, you do not want your jet engine heating up, so you want to be in low soot conditions. So this combination of chemistry, of fluid mechanics, and of the materials properties is very important. The move towards more ceramics in aircraft propulsion systems is another pointer to that. Thank you.
Thank you. So Phil, thank you very much for your talk. I really enjoyed it. Thank you.
Thank you.